Welcome to Getting Started with SOLIDWORKS Simulation. My name is Stephen Petrock, and I'm a product specialist at TriMech, working in our South Florida office here in Fort Lauderdale, Florida. Now, this is my 9th year presenting at 3D Experience World, and I always enjoy the opportunity to share some simulation content with you. I've done many advanced topics, high-level topics, some hands-on sessions, and between you and I, my favorite is always the introductory 101 level classes like this one, Getting Started with SOLIDWORKS Simulation. We are going to talk about 3 things. You're going to leave this session knowing exactly how to get started with your simulation. You'll also learn a lot of tips and tricks on meshing, one of the more integral steps when it comes to getting a simulation going. And then lastly, we're going to focus a lot on your accuracy of your results. But the main core purpose of this presentation is to give you a solid foundation with SOLIDWORKS Simulation so you're able to get started immediately in using this tool. So with that being said, let's get started. I'm going to get started with this bracket, and I want to just find out how much weight this bracket can hold. It's as simple and straightforward as it gets. We're an engineer or a designer using this tool. We have our model. We need to know, will it support the load or weight that it's going to be requested of it? So how do we get started? Well, the first thing you have to do is turn on simulation. How do you do that? Well, as with anything when it comes to doing modeling in SOLIDWORKS, there's many different ways to do that. So we can go up top here to the drop-down menu and hit add-ins, and then you'll be presented with your list of add-ins. You can check the box here to turn it on for this one time, or over here to the right, turns it on from startup. Every single time you launch the software, the add-in will be loaded. The way I like to do it is a little bit quicker, and it's right from the command manager. SOLIDWORKS Simulation right here. I hit the command on the command manager. It takes a second or so, and then simulation is loaded. How do I know it's loaded? Well, I can see it. I see it in my command manager ribbons. If you don't see it in your command manager, well, it's not turned on, so you got to turn it on. Now, did you guys notice that my command manager is collapsed like that? How cool is that? Welcome to 2021. You can collapse or expand your command manager. This is one of my favorite enhancements of this. You know, really, after you've been using the tool for many, many years, it's the little things that really just spice it up and make you fall in love with the tool all over again. Now, how do we get started with simulation? Well, here you have to press New Study because you don't see any other buttons, any other commands. If you look up at the top, there's nothing going on here. You don't see any commands or any buttons. So let's get started. New Study. Now, with that being said, we then get presented a list of more options. Now, for this introductory presentation, we're going to focus more on the first level here, static. Okay? Check the box. We're good to go. Now, our command manager has a lot more buttons. Look at all these buttons here. That's your key that you're in the right spot, the right place in the software, your indicator that you're in the right place, because you see a lot of buttons, a lot of things that you can click on. If it's grayed out, you know, that's SOLIDWORKS' way of telling you, hey, probably not in the right spot. You need to be looking elsewhere. So let's get started with this setup. And the way I like to look at simulation is I like to start at the top right here, and then I work my way down and I hit every one of these. So I look at it as a list, 1, 2, 3, 4, 5, and then run, okay? So start at the top, work our way down. What's at the top? Well, notice this is the same name as the model, okay? It takes the name of the model if it's a part, the body, there's multiple bodies, okay? So here I see the name of the file, I see the material, I see the mesh type, element type. So there's a lot of information going on here. Do you see it? Well, probably not. So let's talk about that. So first thing, this right here, that tells me that it's a solid element. That's the symbol for solid element. This right here tells me it's high quality elements, not draft quality elements. Now that's in addition to, I believe, SOLIDWORKS 2019, maybe even 2018, but it's a recent addition here to the tool. So keep your eye out for that new symbol next to the name. And then to the right, that's the material. So let's start with the material. Right click on it, apply, edit material. Now I'm presented with my list of materials. Let's just go with an aluminum bracket, 6061, T6. Now, you'll see a bunch of different colors here, red or blue. Red tells you you need to know that material property. So I need to know elastics modulus, the elastic modulus, or Young's modulus, Poisson's ratio, mass density, yield strength, or maybe the blue ones, thermal expansion coefficient, for example. If I have a temperature load applied, I'll need to know exactly what value that is. If I have no temperatures applied, there's no thermal expansion. There's no need for the thermal expansion coefficient. Does that make sense? Good, I can hear your heads nodding. That's a joke, I can't. So apply, close, and now we're moving forward. The next step is to still look at the element type and just verify that it's correct. This is a solid, okay? It's a solid geometry. It's an extrusion. It's thick. It's bulky. Perfect for a solid tetrahedron element. Now, if it's something like a surface model or a sheet metal model, something that's very thin in one dimension, say the thickness, for example, and then the length and width are much larger, then maybe a shell element is a little bit more appropriate. Or if it's thin or small in 2 dimensions, right, length and width, and then depth, like a weldment, for example, you can use beam elements. So here we're using solid elements, and that works for us. The next symbol we need to talk about here in step 1 is the blue symbol, letting me know that it's a tetrahedron, a high quality element type. I could change it to be draft quality. I right click, see how the lines are a little bit straighter? That's the difference between high quality and draft quality elements. So I will draw it. Elements in SOLIDWORKS Simulation are tetrahedrons. What's a tetrahedron? Well, not what I just drew. Here we go. What is a tetrahedron? Well, a tetrahedron is like a pyramid, except instead of the base being a square, it's a triangular base. So what I just drew, imagine these line edges are straight. That's a draft quality element. It has nodes here, 1, 2, 3, 4 nodes, and straight lines connecting it. If you switch then to high quality elements, what you do is you add what we call a mid-side node, middle of every element side. Now, there's 6 sides, so it's 6 additional nodes. That gives us a 10-node element as opposed to a 4-node element. What that allows you to do is then have this definition of these element edges be curved or parabolic. So the implications there are actually pretty significant. Because it's a parabola, let's just do a basic parabola, y equals x squared. Here with the 4-node draft quality, we have the geometry as just a linear definition. You know, it always goes back to math, huh? So we're looking at the actual function defining the geometry. Now, this is important because this gets taken into as an input of simulation. And then we define the displacement of it. How does it change over a load, a pressure, a force, okay? And now that change in shape, what we're calling a displacement, can then be turned into a strain result and then a stress result. But what you get is a derivative of this doing a calculus operation. So then it becomes the derivative, first derivative becomes then a linear derivative, or this then becomes a constant. So when you do this calculus operation here, which is going on behind the scenes, whether you like it or not, you're going to get a definition here in the stress as being a linear stress field or a constant stress field throughout the element. So you can see the implication here in just the definition of the geometry, just by setting yourself up that way, gives you more accuracy in a 10-node element. So then everyone says, hey, Stephen, why not use a high-quality 10-node tetrahedron all the time? Well, I'll tell you why. Because it's not free. Now, you have 3 degrees of freedom, x, y, z, in each node. So each equation is solved in each one of those degrees of freedom, x, y, z at each node. So you have 30 equations versus 12 equations up here, right? So a linear element has just 12 equations. So you've then more than doubled the amount of equations that are going on in your matrix. So that means it's going to take a lot longer to solve. So it's not free. When would you use which? Well, if you think you have a simple, straightforward simulation, then absolutely go with a 10-node, high-quality element, which it is by default, mind you. I don't have to do anything. If I weren't teaching you this right now, I would have blasted right past this and not even spent time talking about it. But the meshing is so important when it comes to finite element analysis or SOLIDWORKS simulation that you can't help but begin to talk about it immediately on step 1. It is so integral, so core to the very essence of SOLIDWORKS simulation or FEA that, that's the E in FEA. It's core right there in the actual name of it. So if you want to have a much more complicated simulation, then I recommend switching it to draft quality elements. If you think it's pretty straightforward, pretty basic, you can go ahead and do a high quality element right from the get-go and you're good to go. Okay, so that's step 1. What do we do in step 1? We define the element type, solid. Don't need to do anything because simulation takes that automatically a lot of the time. Sometimes you might want to do, shells or beams. Here's how you can do that. I can define it as shells or I can treat it as beams. There's your other 2 element types. I wouldn't recommend doing that because a lot of the time, simulation knows exactly how you modeled it, exactly what the shape of it is. And with that being said, it's able to make the right decision intelligently for you so you're off and ready to go. Now, let's move on from step 1 and on to step 2. And we'll make up time here because we don't have to do anything. Connections. Connections is how multiple bodies interact with one another. We're getting started here with lesson 1 being a simple bracket, a single part, a single body. So there is nothing else for us to do. We can move on from there. Now, fixtures. Here we right click and I need to define how this is held in place. How does it interact with everything else in the environment that's not modeled? So my bracket is going to be held up here. Maybe it could be held here too. This is fixed, okay? Anything that's on this face is not going to move. Maybe, for example, I want to say, okay, it's being held in place there, but it's up against a wall, okay? So then I'll add a roller slider here. Now, check out the image, right? I want you to look here, okay? See how it's spinning around or it's not moving at all, or maybe it's rotating about an axis. It's giving you a preview of the fixture and what it's doing to the model. So we'll go with a roller slider here. Maybe we won't. Just hit the X and get out of there. It's up to you. Is it just held up in the top? Is it held only here and just left in space and you have a load on it this way? Or is it up against a wall? What you have to do is capture virtually here what is really going on in the real world. Okay? It's up to you. No one knows your models and what's going to happen to them more than you. So with that being said, you have to work to capture everything that's going on in the real world here virtually using this tool. So there's my 2 fixtures. I'm happy with that. We're moving on now. We did 1, 2, 3. Step 4, external loads. Again, notice how all of the work I'm doing is down here in the side. I keep stepping down item by item, right-clicking on each one of them to get access to the menus. I right-click, I hit force. Now, SOLIDWORKS simulation is very graphical. I wouldn't get caught up on the directions being X, Y, and Z. Rather, focus more on the arrows and the directions that they're pointing. Those are very important indicators telling you exactly how the simulation is going to behave. whether it's fixtures, whether it's loads, those arrows give you the information on what you need to know. Because like, what if it's negative 15 and then I reverse the direction? You got to not really get caught up on the absolute values here and the directions and the magnitude of it, but rather the visual cues here from the arrows. So here's my loading on that face, but I don't want it going, the only thing I can do here is just reverse the direction, in, out, in, out. That's because it is normal to the selected face. Now, if I want it in a particular direction, I hit selected direction. Now, I have a reference. This reference can be a sketched line. It can be a model edge, a face, a plane, anything that I can then reference to define the direction. So notice here, by default, it gives me 3 options, 1, 2, 3, 3 directions. If I pick a plane, 1, 2, 3 are still there. If I clear that and then I pick a line, it then recognizes it as being a linear entity, and I only have one option. So be smart in what you pick. If you pick a face, then you have an extra click. No, not that. So this is the force is applied here, and then select a direction. If I pick a face, then I have to do a little bit more work. But if I click a edge that defines the direction, luckily I have an edge going in that direction, I can then key in the appropriate value here. About 15-pound bracket. See how it does. All right, check mark. And that's it. So now the last step is to create the mesh, but you know what? I don't even have to do that. I can just run the study. I hit run, and we're good to go. Now, let's take a look at it. We'll right-click on my results. I'm going to animate it to just first things first, look at it. And wow, that is crazy. How is this bracket wobbling so much? Well, I'll tell you how. The deformation scale, 717. Let's change that so it's true scale. And then maybe we'll get a better indication on the deformed shape. So definition of the plot, I right-clicked on the plot. I'll do that again. That was a little quick. Edit definition of the plot, true scale. There we go. Now I'll animate it, and we probably won't even notice it. Yep, all we're noticing are the colors changing. The shape of it's not actually changing. Not at all. All right. So now that we have that done, I can start to change this around. So I'll double click on my plot here. Since I'm a normal person, I kind of like floating instead of scientific notation. And then the yield strength, this is an important indicator here. It tells us the maximum stress that this thing is able to take without breaking. So I want to keep it below that. But I do 275, what is that? Million? Numbers, I don't know. Not a numbers guy here. I don't like doing math. Luckily for us, there's a plot. Right-click on results, and I can define a factor of safety plot. Hit the check mark, and now, always with the scientific notation. Love it. Now it's telling us how much loading can this take? 72.5 times that. So if this really was a 15-pound bracket, I think I'm going to be okay. Would you guys agree? Again, the head's nodding. I hear it. Great. So that was really the main goal here, was to show you how to get started with a simulation. All right. So again, let's do that one more time. New study. And then we start at the top, work our way down. It's solid, high quality material, right? Solid elements, high quality mesh. This is the material. I right click on it, apply, edit the material, aluminum, 6061. Maybe right click and add to favorites so that you can then apply, close it really quickly from here. 6061, right there all the time. Fixtures, well, I skipped step 2 because I didn't need it. Hit here, I'm going to pin that. Check, roller slider, check. Get out of there. External loads. Remember, a force, it was on this face in a selected direction. I selected this direction, SI, 15 pounds. run it like that, okay? What happened? Well, I was going too quick and I wasn't looking at the arrows. So what I need to do is edit the definition of that force and reverse the direction. Okay, I'm going quickly here just to let you guys know exactly how long this. So far, we've been here for what, 15 minutes of simulation? It should take you less than a minute to set up the most basic of studies, the absolute most basic of studies, okay? So now let's do it one more time and let's start talking about some tips and some tricks. Okay, I want to go back to the first one, and you know what I really liked? The way I defined this fixture and this loading. So what I can do is I can click each one of them and copy them. I can drag and I can drop them onto it. But that required that I had a study already set up. You can right click on it and do copy study. You can even extend it to be a nonlinear linear dynamic study, right? So I can give it a name, copied. Very good. Okay, so that was the copied study. Now, what are some things that I can do here to change this? Well, let's go back and look at the mesh. If I right click on mesh, I create the mesh. I have this slider here. Let's start. We're looking at this right now. This is the most basic or simple interface for meshing with just a mesh factor. Now this is the slider, okay? Mesh factor, fine or coarse, okay? And reset. Notice there's no numbers here, right? It's just fine and it's just coarse. This is unique to every single model. Fine means something for only this model, and coarse means something only for this model. The next time you load a different model, fine and coarse will mean different things. There'll be different sizes. This is all based on the overall shape and size of your model with an algorithm that looks at the geometry itself. So this is not always 10 and 1 and 100, right? It's unique to every single model. So I'll go to the fine. That makes the triangles much smaller. Let's take a look at it. Oops. Fine looks like that. You know what? And then if I want to go even finer, we'll go with 1. So I can key in the numbers here, but I need to be able to see that, right? So extend it, and then 1, and then you know what? I'm going to grab this. There we go. Here's the dialog box that's up on my other screen here. So now we can see it. So finer refers to the mesh size, okay? The element size. The elements themselves are finer. They're smaller. That means there's more of them. And you can see you're actually able to look at the slider now this time. Before, the slider was so quick. The mesh dialog, rather, status bar was so quick you couldn't even see it. But here is my 1 millimeter size. So that's fine. Let's go back. Coarse. Ooh. Now, what you really need is at least 2 elements between the thickness of this. So here's 2 elements. I need more than that. This is only 1 element. I would say go for 3 elements across the thickness, okay? We say 2 high-quality elements across the thickness. You could probably get a little bit more than that, okay? You can try to get more than just 2 elements across the thickness. But notice how, reset right in the middle, if I have this in the middle, it's spot on. 1, 2, 3, 4 across the thickness. So that's pretty good to me. All right, perfect. Let's talk a little bit more about the mesh. So I have these different algorithms here, right? So here's basic, entry level, starter, meshing interface. I expand this. I then get blended curvature based, or standard. Standard just is triangles, right? Here's the triangle size, element size, and then a tolerance. If the nodes are within that certain range, it will then merge them together into one element. And then you also have the Jacobian. Jacobian is something you don't need to worry about. In my many years of doing this, Jacobian's never been an issue. Jacobian is just a check for distorted elements, right? Here's a regular element, and here is a distorted element. See how they cross over each other like that? That is a distorted element. That is not what we want. But we're using the auto mesher. This auto mesher is so powerful, so robust that I, in my over a decade of experience using this tool, have never once ever had an issue with that. So curvature-based mesher, it's good. It's a different algorithm. It gives you the ability to have a max and a min size. Okay, so I can say the minimum elements I want to be 1 and the max element I want to be 3. So then it gives it more of a range, okay, where it can grow or shrink. It's a little bit more dynamic, okay? It looks at the accuracy of the mesher and then defines it. How does it know where to put a big element and where to put a small element? Well, that has to do with a actual quantity of the element that we call the aspect ratio, okay? That goes to the quality of it. Now, it's an actual quantity. It's something we can quantify. We can say yes or no if an element's good based on a particular number. Now, I'm going to do this in just 2D because it's much easier to explain. A element's aspect ratio is the ratio of this line height to the base. Okay, I like to think of it that way, but because a tetrahedron is truly in 3D, like this, it actually goes from one side to the opposite side, opposite side, opposite side, and it's the ratio of the longest to the shortest one of these. An aspect ratio of 1 is a perfectly shaped triangle or element, tetrahedron. Okay? I sometimes use those terms interchangeably because we only see the surface, the outside surface of these tetrahedrons. So they basically, I mean, to me, they're triangles, but they're obviously not. They're 3D. We live in a 3D world. Simulation is a 3D product, a 3D tool in 3D space. So I'll call them tetrahedrons. But please don't hold me accountable for calling it a triangle, okay? Then an aspect ratio of 1 is a perfectly shaped one. An aspect ratio of bad, or like 10, 15, is something like this. Really long and a really short gives you a really bad shaped element, right? I'll use this symbol for bad and then this symbol for good. Okay. So that's what aspect ratio is. Well, I could look at this and I can say that's pretty good, but you can also start to see some elements that might not be so good, right? So here, for example, this is a little bit longer and shorter than this. This is a perfectly shaped element right there. See how nice and more or less like an equilateral triangle? If it were in 2D space, mind you, it'd be that. Now, how can I tell? There's a lot of elements here. What do these look like from a mesh quality standpoint? Well, I right-click on Mesh and I go to Details. This tells me all the information I need to know. I can look at these numbers and tell you whether or not it's a good mesh or if it's a bad mesh. So here's what I look for. Total number of elements or nodes. These tell you how many equations are going to be solved in the problem. And if it's too high, then it won't solve. If you have 1 million nodes, your computer is going to lock up instantly. And you probably won't ever solve that. So that tells me, okay, 60,000 nodes, 57,509. I could solve that, no problem. The max aspect ratio, the next one, that is the most distorted element. And that's really good. If you have an aspect ratio, a max aspect ratio less than 10, you have a good mesh. If you have a max aspect ratio of 3, you have the best mesh ever. Because it has to do with, I keep hitting escape and getting out of here to clear my drawings. You have 99.9 with an aspect ratio less than 3. If this number should be in the 90s, okay? This number should be less than 10. It could be less than 20. So let's go back here. It shows you how to get started. Talked a lot about meshing. And we also talked about some tips and tricks for the accuracy of your simulation. There is a lot to cover when it comes to a tool like SOLIDWORKS Simulation, but I hope you enjoyed this presentation about how to get started with SOLIDWORKS Simulation. Again, my name is Steven. I appreciate you joining me for this interesting 3D Experience World 2021. Again, I always enjoy the opportunity to share the simulation content with you guys because it's an amazing tool, and I think it should be in the hands of every designer using SOLIDWORKS. Thank you.